Welcome to our channel, Nano Raj Tech. Today we discuss about Introduction to Machine Learning, Part 1. Hope you are enjoy. Please like, share and subscribe our channel. Here we discuss about the topics, Introduction to Machine Learning, Types of Machine Learning, Key Concepts in Machine Learning, Philosophy of Learning in Computers, Ethical and Social Considerations and Overview of different forms of machine learning. Let us we start. Introduction to Machine Learning. Machine learning, ML, is a subset of artificial intelligence, AI, that enables computers to learn from data and make decisions without being explicitly programmed. Machine learning algorithms identify patterns in data and improve their performance over time as they are exposed to more information. Next we discuss about types of machine learning. 1. Supervised learning. 2. Unsupervised learning. 3. Reinforcement learning. Then we discuss about each one. 1. Supervised learning. In this supervised learning, the algorithm learns from labeled data, input-output pairs, example algorithms, linear regression, decision trees, neural networks, and applications are spam detection, fraud detection, sentiment analysis. Next, 2. Unsupervised learning. In this unsupervised learning, the algorithm explores data without predefined labels and finds hidden patterns. Example algorithms, K-means clustering, principal component analysis, PCA, and applications are customer segmentation, anomaly detection, recommendation systems. Next. Reinforcement learning. In this reinforcement learning, the algorithm learns through trial and error, receiving rewards or penalties. Example algorithms, Q-learning, deep Q networks, DQN, and applications are robotics, game playing, e.g., AlphaGo, autonomous driving. Next we discuss about key concepts in machine learning. In this, first one, training data and test data. Data is split to train models and evaluate performance. Next, features and labels. Features are input variables, and labels are the target outputs. Next, overfitting and underfitting. Overfitting occurs when a model learns noise. Underfitting occurs when it fails to capture patterns. Next, evaluation metrics. Accuracy, precision, recall, F1 score, RMSE, root mean square error. Next we discuss about philosophy of learning in computers. The philosophy of learning in computers explores the fundamental principles, theories, and conceptual questions surrounding how machines acquire knowledge, adapt to new information, and simulate human-like learning processes. It draws from disciplines such as artificial intelligence in short form AI, cognitive science, epistemology that is the theory of knowledge, and philosophy of mind. Next we discuss about key philosophical questions in machine learning. 1. What does it mean for a machine to learn? Human learning involves understanding, reasoning, and intuition, whereas machine learning typically involves statistical pattern recognition. Can machines truly understand, or do they merely process data and optimize based on patterns? Next, 2. Is machine learning truly intelligence or mere computation? Philosophers question whether machine learning systems demonstrate genuine intelligence or if they are just highly sophisticated data processing systems without awareness or intentionality, the ability to have goals and purpose. 3. Can machines develop knowledge autonomously? Traditional epistemology argues that knowledge requires justification and belief. Do machine learning models know things, or are they just approximating reality based on correlations? Next. 4. Bias and fairness in learning algorithms. Since machine learning models learn from human-generated data, they may inherit biases. Philosophers and ethicists debate whether machines can ever be truly fair and how we should address algorithmic bias. Next. 5. The nature of consciousness in artificial intelligence AI. Could advanced learning algorithms one day develop self-awareness, or will they always remain tools with no subjective experience? A key question in consciousness studies and the hard problem of artificial intelligence. Next, philosophical theories relevant to machine learning. 1. Empiricism versus rationalism. Empiricists, example is John Locke, David Hume, argue that knowledge comes from experience, which aligns with machine learning models that learn from data. Rationalists, example, Descartes, emphasize innate knowledge and reasoning, suggesting artificial intelligence AI might need built-in frameworks to truly think. 2. Functionalism in artificial intelligence AI. This theory argues that mental states, such as beliefs and desires, are defined by their functional role, not by their physical makeup. Under this view, an artificial intelligence AI could be considered intelligent if it performs human-like cognitive functions. 3. Symbolism versus connectionism. Symbolic artificial intelligence AI, rule-based systems, represents classical logic and reasoning, while connectionist artificial intelligence AI, neural networks, models learning based on brain-like structures. The debate continues on which approach better simulates real intelligence. 4. Turing test and Chinese room argument. Alan Turing proposed the Turing test as a measure of machine intelligence, while John Searle's Chinese room argument challenges the idea that processing symbols equates to understanding. Next, ethical and social considerations. 1. Accountability. Who is responsible when an AI system makes an error? 2. Transparency. Should machine learning models be explainable, or is a black box approach acceptable? 3. Autonomy versus control. To what extent should artificial intelligence AI systems make decisions independently? The philosophy of machine learning raises deep questions about the nature of intelligence, knowledge, and consciousness. While machine learning systems excel at pattern recognition and decision-making, whether they can truly learn in the human sense remains a profound and open question. Next, different forms of machine learning. Intelligent systems, such as autonomous robots, smart assistants, and adaptive control systems, rely on machine learning to perceive, reason, and make decisions. Machine learning enables these systems to learn from data, improve their performance, and adapt to dynamic environments. These are 1. Supervised learning, 2. Unsupervised learning, 3. Semi-supervised learning, 4. Reinforcement learning (RL), 5. Self-supervised learning, 6. Online learning (incremental learning), 7. Transfer learning, 8. Evolutionary learning (genetic algorithms), 9. Federated learning. Here we discuss one by one. 1. Supervised learning. Supervised learning involves training an intelligent system on labeled data, where input-output pairs guide the learning process. Key characteristics. Learns from known examples, input features and corresponding labels. Requires a large amount of labeled data. Evaluated using metrics such as accuracy, precision, recall, and F1 score. Example algorithms. Linear regression, logistic regression, support vector machines (SVM), neural networks e.g., CNNs for image recognition. Applications in intelligent systems, autonomous vehicles, object detection and lane tracking, healthcare, disease diagnosis based on medical imaging, voice assistants, speech-to-text conversion. Next, 2. Unsupervised learning. Unsupervised learning is used when the system must find hidden patterns or structures in unlabeled data, meaning no explicit instructions are provided. Key characteristics. Finds underlying structure and relationships in data. Used for clustering, dimensionality reduction, and anomaly detection. Example algorithms. K-means clustering, hierarchical clustering, principal component analysis (PCA). Autoencoders. Applications in intelligent systems. Customer segmentation for recommendation engines. Anomaly detection in cybersecurity systems. Pattern recognition in industrial automation. Next, semi-supervised learning. Semi-supervised learning is a hybrid approach that leverages a small amount of labeled data along with a large amount of unlabeled data to improve learning efficiency. Key characteristics. Helps when labeling data is expensive or time-consuming. Achieves higher accuracy with fewer labeled samples. Combines aspects of supervised and unsupervised learning. Example algorithms. Self-training models. Graph-based semi-supervised learning. Variational autoencoders (VAE). Applications in intelligent systems. Medical diagnostics with limited labeled patient data. Fraud detection in financial transactions. Speech recognition with partial transcriptions. Next, 4. Reinforcement learning (RL). Reinforcement learning (RL) enables intelligent systems to learn through trial and error, optimizing actions to maximize rewards over time. Key characteristics. Works based on rewards and penalties. Agent interacts with the environment to learn optimal policies. balances exploration, trying new actions, and exploitation, using known actions. Example algorithms. Q-learning, deep Q networks, DQN. Policy gradient methods, example, PPO, A3C. Actor-critic methods. Applications in intelligent systems. Robotics, training robots for autonomous navigation. Gaming, AI systems beating human players, example, AlphaGo. Industrial automation, optimizing energy consumption in smart factories. Next, 5. Self-supervised learning. Self-supervised learning allows intelligent systems to generate their own training labels from raw data, reducing reliance on human-labeled datasets. Key characteristics. Uses pretext tasks, example, predicting missing parts of data. Often used in natural language processing, NLP, and computer vision. Improves data efficiency in generalization. Example algorithms. Contrastive learning, example, SimCLR. Masked language models, example, BERT. Generative models, example, GANs. Applications in intelligent systems. Language understanding, example, GPT models. Image and video recognition. Predictive maintenance systems. Next, online learning, incremental learning. Online learning allows intelligent systems to learn continuously from streaming data, adapting to new information without retraining from scratch. Key characteristics. Processes data in real time or sequentially. Useful for dynamic environments with evolving patterns. Suitable for resource-constrained environments. Example algorithms. Stochastic gradient descent, SGD. Perceptron learning algorithm. Passive-aggressive algorithms. Applications in intelligent systems. Stock market prediction systems. Adaptive traffic management systems. Real-time fraud detection in financial systems. Next, 7. Transfer learning. Transfer learning allows an intelligent system to leverage knowledge learned from one domain and apply it to another related domain, reducing the need for extensive new training. Key characteristics. Useful when data is scarce in the target domain. Reduces training time and computational costs. Fine-tuning pre-trained models is a common approach. Example algorithms. Pre-trained deep learning models, example, ResNet, BERT. Domain adaptation techniques. Applications in intelligent systems. Using models trained on general images to identify medical conditions. Applying autonomous driving models across different environments. Speech-to-text models adapted for different languages. Next, 8. Evolutionary learning, genetic algorithms. Inspired by biological evolution, evolutionary learning uses genetic algorithms and evolutionary strategies to optimize solutions for complex problems. Key characteristics. Based on natural selection principles such as mutation, crossover, and selection. Suitable for optimization problems with large search spaces. Can be combined with other machine learning techniques. Example algorithms. Genetic algorithms, GA. Particle swarm optimization, PSO. Differential evolution, DE. Applications in intelligent systems. Designing optimal mechanical structures. Tuning hyperparameters in machine learning models. Robotics path planning and control. Next, 9. Federated learning. Federated learning enables intelligent systems to train models across decentralized devices while preserving data privacy. Key characteristics. Data remains on local devices, only model updates are shared. Reduces privacy risks and improves compliance with regulations. Useful for edge computing applications. Example algorithms. Federated averaging, FediVG. Secure aggregation techniques. Applications in intelligent systems. Healthcare applications with sensitive patient data. Personalized artificial intelligence AI assistants across mobile devices. Smart city applications with distributed Internet of Things, IoT sensors. Hope you are enjoy. About Introduction to Machine Learning, Types of Machine Learning, Key Concepts in Machine Learning, Philosophy of Learning in Computers, Ethical and Social Considerations and Overview of different forms of machine learning. Thanks for watching our channel. Nano Raj Tech. Please like, share and subscribe our channel for more videos. Thank you.